Now I am trying to put this to your book notation. So in your book notation, c times t is x0, that is the time coordinate, and v over c is called beta, the magnitude of this beta square, and what else? Just a second. So we have gamma square as a Lorentz factor. So that stuff square root of 1 minus v square is gamma, which is called Lorentz factor, that is 1 over 1 minus beta square. So we denote the geometry is in the following. We have space and time coordinate k and k prime. It could move to each other with some velocity or beta. If the motion is along the x direction, so one coordinate x will be transformed and time coordinate will be transformed as a Lorentz transformation. So basically, the first term will be represented as in the following. So multiply both sides by c. That will be ct prime. Ct prime is called as a x0 prime. So if you multiply one of the c there, that is ct prime in your book presentation. And the leftover is c times t. So this is gamma 1 over 1 minus v square over c square, and c times t is x0 ct, and what is left here? V over c is left. V over c magnitude is beta. X is the x1. So basically, you have here x0 prime, x1 prime, x2 prime, and x3 prime. These are the 4 vectors of the space, time and space coordinates with respect to the k prime observer. With respect to the k observer, so suppose that you are observing somewhere here. With respect to the k prime observer, we have x0 prime, x1 prime, x2 prime, and x3 prime. With respect to the here, you can write this the 4-dimensionally. That is nothing but x0, x1, x2, and x3. So this is the Lorentz transformation of the time coordinates. So let us look at it again. C times t prime is x0 prime. C times t is x0. This bunch is the gamma factor. V over c is beta. X is the x coordinate. So x1. So x is the x1. x1 prime, x1 prime is nothing but gamma, this factor, and x is x1. minus Vt multiplied by C divided by C, that is nothing but beta x0. This term is equal to V over C times Ct. This is x0, this is V, this is beta. So if these two frames, this was an example in one dimension, if the two frames are moving relative to each other in one dimension along x, the perpendicular coordinates doesn't affect it from the Lorentz transformation. So basically x2 prime will be x2, x3 prime will be x3. So if two observers moving with respect to each other along x direction, time coordinate is affected. Along the motion, the coordinate is affected, but the perpendicular coordinates doesn't affect it from the motion, so they will stay additive. So this whole thing is the Lorentz transformations. So you can write the inverse Lorentz transformation easily. So all you have to do for inverse Lorentz transformation, inverse Lorentz transformation, what you have to do, replace the prime as an unprime and make the velocity invert the direction of the velocity. So that will be x1 gamma x1 prime plus beta x0 prime. These are not affected. So one is the Lorentz transformation, the other is inverse Lorentz transformation. In general, you can write the Lorentz transformation in vectorial form for the Cartesians, and for the time coordinates, you can write the Lorentz transformation. So let us write the Lorentz transformation in the vectorial form. So if k prime is moving with respect to the k with some velocity, you can decompose the point of interest parallel to the motion and perpendicular to the motion. Parallel to the motion is transformed like this. Perpendicular to the motion does not affect it. So the situation will be the following. If you want that the x observed from k prime, you can say that let have my vector has the parallel to the motion and perpendicular to the motion. So we denote in that form. Okay. So for the perpendicular to the motion doesn't affect it, and you can say that this will not be affected. That is nothing but x perpendicular, but x parallel will be affected in that form, and that will be equal to gamma x parallel minus beta x0. So which one I wrote? This parallel gamma x parallel minus beta x0. So add up x parallel and x subtract the x parallel. So these two will be the x prime will be what? x. This is the x from seen here. This is the x prime seen from the k prime. So these two will be x. The leftover terms will be plus gamma minus 1 x parallel and minus beta gamma beta x0. And you can write the x parallel. So basically v and beta are the same thing. V over c is the beta. So you can write the x parallel in general x dot product beta over beta unit vector, projection of the x along the beta unit vector times the unit vector itself. This is the x parallel. X parallel is the projection of the x to the beta because the frame is moving along the beta. Okay, we have x. If the beta is in this direction, this is the projection of the x along the beta. So then you can write the time coordinate in 3 dimension. So the time coordinate, here's the time coordinate. This is the time coordinate. So the time coordinate, so this is the space coordinate transformation. The time coordinates will be x0 prime, gamma x0. This was beta. No, this is the time coordinate. I am sorry. So I am sorry. Right, this is yes, gamma x0 minus beta x1. So beta x1 is nothing but projection of the x along beta. That corresponds to beta x1. So this is the Lorentz transformation in 3 dimension and the time coordinate. If you want the inverse Lorentz transformation, make this unprime prime and replace the velocity as a minus. I want to show you another thing about the Lorentz transformation. You can, as I said to you, that is the hyperbolic transformation. It's called hyperbolic transformation. So if you call the beta as a tangent hyperbolic psi is called a boost parameter or rapidity, and gamma is cosine hyperbolic psi, and gamma times beta is nothing but multiplication of this sine hyperbolic psi, and psi is called boost parameter. The situation is the following. You can write this Lorentz transformation, let's say, in one-dimensional motion of the frames in the following form. So x0 prime is equal to what? X0 prime is equal to, where is the gamma? Gamma is cosine hyperbolic eta times x0 cosine hyperbolic psi times x0, instead of gamma, say cosine hyperbolic psi, minus, instead of beta gamma, that is nothing but sine hyperbolic psi x1, x1 prime is equal to what? Gamma x1. Gamma is cosine hyperbolic psi x1, and minus gamma beta is sine hyperbolic psi x0. So, and x2 prime is equal to x2, x3 prime is equal to x3. So did I write this correctly? I think it should be cosine, sine. Okay. You can write this in a matrix presentation in the following. So what is the matrix presentation? x0 prime, x1 prime, x2 prime, x3 prime. And here you have x0, x1, x2, x3. What is the matrix form here? So I haven't placed here. So this will be cosine hyperbolic minus sine hyperbolic. This should be cosine. So I will write it again. So I have to write again. Sorry about this. x0 prime, x1 prime, x2 prime, x3 prime is equal to what? x0, x1, x2, and x3. And this is nothing but one-dimensional boost along x1. And if you adapt these things, so what should be this element? Cosine hyperbolic eta. And x1 should be minus sine hyperbolic psi. So psi, sorry about this. The other terms, 0 and 0. And for that one, this should be multiplied x0. There should be minus sine hyperbolic psi, and the other one x1 times cosine hyperbolic psi. This should be 0, 0. And how about the other terms? 0, 0, 1, 0, 0, 0, 0, 1. So this is the transformation of the Lorentz transformation in terms of the boost matrix in one dimension. If you multiply this column and this row, you can obtain this. If you multiply this column with the second one, you can obtain the second and x. And what happens? And this is equal to x equal to ct, as I said earlier. If you apply this, that does not rotate the coordinates, that makes some boost in that direction. So this becomes ct prime, this becomes x prime, and this angle is psi. Okay? Now, in general, you can have not only space and time, you will have other four vectors: energy, momentum, four wave number, four-dimensional Lorentz force, and so on. So in any case, if you have any four vector, you can write the Lorentz transformation in the following form. So if you have any four vector, let's say A0, A1, A2, and A3. So this will be the first one, will be the time coordinate, even though it is not the time coordinate, we will call the time coordinate. That could be energy, momentum, and another thing, but we will call that the first one, or zeroth one, let's say zeroth one is a time coordinate, and A0 prime will transform as gamma A0 beta dot A, and the perpendicular to the motion will transform gamma, so parallel to the motion, I am sorry, gamma A parallel minus beta A0, and the perpendicular component of the coordinates relative to the motion will not be affected. So anyway, if you have any 4 vector, you can apply the Lorentz transformation. So the other property is the following. If you have a length of the 4 vector, in any Lorentz transformation, the length doesn't change, and the length is defined in the following way. That is important. So it is called a scalar product. What I said that in the beginning, c square t square minus x square y square plus z square is equal to c square t prime square minus x prime square y prime square plus z prime square. For any vector, the scalar product, which is called in that form, is invariant. So if you look at the scalar product of the vector, 4 vector, which is denoted by E dot A. So in your book notation, yes, is nothing but A0 square minus A square. This is the scalar product of the A by itself, the length of the A square. In any Lorentz frame, that length doesn't change. So that is equal to, if you apply a Lorentz transformation to here, and if you look at that length, that will be the same. So A0 prime square minus A prime square. So this is the scalar product of the 4 vector by itself. If you have a 2 4 vector, A dot B, and that is again very simple. So first multiply the first coordinates of the A0 and B0. Then look at the A dot B. And if you go to another Lorentz frame, if you make the Lorentz transformation of A and B, so in different frames, you have A prime 4 vector and B prime 4 vector. If you look at the scalar product, that will be A0 prime, B0 prime minus A prime dot B prime. So scalar product is an invariant. Okay. So this is very important because we can use this in the light cone, and we can look at the light, time light, and space light separations and do lots of things. This is very important. If you have a 4 vector, if you have another 4 vector, if you make a Lorentz transformation to both 4 vectors, if you look at the scalar product in one frame and the other frame, they will be the same. So this is the key point. So what is done? Now we can plot the light cone CT in 1, and we can plot X. We cannot plot in 4 dimensions. Let's say you plot X, Y, and Z, whatever. So basically, the separation is the following. We have a region. You have a region which is aligned with the CT and X. And so if you have a, let's say, X outside, Y there, you can write X outside, Y there, and this is a cone in 3 dimensions. We cannot plot in 4 dimensions, but up is the time coordinate. So any object has a past and the future. So if you are not moving, sitting here, as time coordinate is gone, you are moving in the light cone in upward direction. So all motions in the light cone from past to future. So using the scalar product, you can define invariance. So basically, if you have 2 events, P1, which occurs at CT1 and X1 in 3 dimensions, and another is C2, X2. You can look at the length of the separation of the 2 events. Length of the separation of the 2 events. So that is nothing but C square T2 minus T1 square minus X2 minus X1 square. All you do, subtract these 4 vectors from each other, look at the scalar product by itself. Okay? This length is the same everywhere. And there are meanings of this. So it is called, let's say, S12 square, that length. The options are the following. S12 square could be greater than 0. S12 square is less than 0. And S12 is equal to 0. So you know that this is the difference of the length of the difference of the 4 vectors. One event occurred T1, X1, the other event occurred T2, X2. One event occurred at T1, X1 in Ankara, the other occurs in Istanbul in different time and space, let's say. So if the difference, length of the difference is positive, the situation is the following. If this is a positive, that will be positive in all inertial frames. This, let's say 5. That will be 5 in all Lorentz frames. And in order to get a 5 positive here, we have a choice that these events occur at the same location in totally different times coordinates. So you can find, let's say this is observed at K coordinate, but you can find a coordinate such that this number the same, events occur at completely different times, but same location in space. because this length have to be the greater than 0. This kind of length is called as a time-lag separation. This one. So maybe I'm thinking this event occur in Ankara, event occur in Istanbul, different times in different coordinates, but in some space shuttle going some velocity, observe that the events occur in totally different place, in Adana, totally different times. So this is allowed. And another thing here, if is greater number, then if you divide this delta t in everywhere, then delta x over delta t should be what? If it's positive, let's say 5, 10, 100, and if you divide everything to the delta t, then what is the condition delta x over delta t? Is it greater than 0 or less than 0?
Smaller than c.
Smaller than c, because this is positive. Yes. So time-lag separation is all the times inside the light cone. Okay. Other one is the opposite. You will guess what will happen. The other one is when you have this case, c square t minus t1 square x2 minus x1 square at k prime, and that could be what? This is negative, then you can find that a new coordinate system, which is t1 prime is equal to t2 prime, and t1 prime is equal to t2, and that is x2 prime minus x1 prime. Since this is the opposite case of this is the region. This is called as a space-like separation. And in the space, since this is the opposite of the time-lag, that is a region outside the light cone, forbidden part. Things are greater than speed of light, and it violates with the causality. The other one, you can guess what is this. When the length is equal to 0, that is called as a light-light separation. And in that case, events are lights on the light cone and connected by light signals. So these are the connection will be on the light cone. So that is light cone separation. So you see that the time-lag separation, space-lag separation, and the light-light separation. Light-light separation is on the light cone, and all property is very simple. Scalar product of the 4 vector is invariant in all Lorentz, all inertial frames. Therefore, differences are same invariant, but the differences has meanings, like time-lag separation, space-lag, and light-lag separations. So let us go over the other properties of the Lorentz transformations. So we will see another quantity now, and we will use this oftenly. You can write that the separation in small, in differential, not the x1 minus x2. Then instead of writing the x1 minus x2, you can write dx or dt. Then c square times the differential amount of change minus dx square should be ds square, and dx is nothing but, let's say, u times dt, u is the speed, and dx square over dx square will be u square dt square, multiply by c, by divide by c, and plug the other up, then ds square will be c square dt square, and this is beta, and that will be what? If you take the c square dt square parenthesis, c square dt square, this will be 1. That is c square dt square, and what is left over? 1 minus u over c. So that is nothing but beta c dt. Take the c square dt square, so that should be this. If you go to a different coordinate system, this length doesn't change. We said that. So if you go to the coordinate system such that c square dt prime square minus dx prime square, this value will be the same. That is again c square dt square 1 minus beta square. So the thing is the following. Every inertial frame has 4 vectors, time and space coordinates. Everything is different. So you need to calibrate the coordinates in the time if you want to make a measurement, let's say for velocity. The usual trick is the following. Generally everybody agrees this one. If dx prime is 0, if the clock with you, we call this dt prime is a proper time. So if the dx prime is 0, ds square is equal to c square d tau square. We call this is the proper time of the source. And that is equal to c square dt square 1 minus beta square. Sometimes they are calling this is a proper length because length or proper time. Okay? So that means that we are all inertial frames in the space. We have coordinates, time coordinates, but I have the clock, and the clock doesn't move with respect to me. So you can use my proper time if you need it. If you make some velocity measurement for velocity, I will discuss this later. So basically, from here, proper time is equal to what? Take the square root of this. C's are cancelled. Proper time is equal to dt square root of 1 minus beta square. And what is 1 minus beta square of square root of? Square root of 1 minus beta square, and that is gamma, or 1 over gamma. And you can take this and you can write that the time interval is gamma times d tau from 1 to the second. So if you have the clock, one is the proper time, clock with you, the other is another observer. All the times moving clock is slower. So that is the time dilation. So one, you know this very well from the undergraduate muon experiments in the atmosphere. When the muons enter the atmosphere, they should decay very rapidly. But the people at the ground, they see that the muons. Why? With respect to us, their clocks are slow. their speed is close to the speed of light. So therefore, their time dilation is like, and the decay times is long with respect to the ground observer. So time dilation or length contraction are equivalent. So if the time is dilated, we can see close to the ground, or with respect to us, either the time is dilated or length is contracted. So, but this is universal. Everybody agrees that proper time or the proper length. If you want to measure, for example, for velocity, how you can make the measurement for velocity? We have space and 4 vectors. What is the 4 vectors? Time and space. Okay. If you want to find the 4 velocity, you should divide these things to the time. But every coordinate has different times. You don't divide every coordinate. You can divide to the proper time, because the proper time is the same for every observer. Of course, we are working on the what? What kind of separation? ds is what? Are we working in the timeline or space-time? Timeline. So for the case of the photon has no clock, it sticks because gamma blows up. Okay. So we learn all tools. So using the 4 vectors and the invariance of the scalar product, we will study that the relativistic Doppler shift. We have a 4 time and space coordinates. We have the 4 energy and momentum. So sorry, 4 wave number. The scalar product will be the phase of the electromagnetic wave. We will see that, and that invariance will give us the relativistic Doppler shift. And we will work on with the addition of velocities next time. We will investigate, we will represent the Lorentz transformations in the mathematical as a covariant and contravariant transformations. Then we will represent all Maxwell's equations and the Lorentz force in the covariant form.